Well, hello there. Welcome to our video on integration fractions. You see, this is our last technique that we'll use to actually find the antiderivative. All right, so we've got lots of techniques we've studied up to this point. We've got substitution, we've got integration by parts, we've got all of our other antiderivatives, which are common antiderivatives. And now we investigate this particular situation when we have a rational function. Okay, so our overview, we're actually only going to do 3 examples today. Because they're actually very detailed as far as the process we're going to undergo to find the antiderivatives of certain rational functions. So in order to integrate certain rational functions, we use this process called partial fraction decomposition. All right, and that is going to be assuming that the function is a proper fraction. Basically what we're going to do is we're going to factor our denominator and figure out what our original fractions were that combined to create this new rational function. So we're decomposing the denominator of a rational function into smaller parts, and then the antiderivative will often involve either rational functions or logarithms or arctangents. All right, so let's dive right into this and see what we're going to do. So our first case is we got a particular rational function that's 1 over x minus 2 times x minus 5. X minus 2 and x minus 5 in our denominator here. And our objective is to see what 2 fractions combined to give us this particular rational function here. So our technique is what's called partial fraction decomposition. The first step that we'll use is we'll say we're going to rewrite the rational as the sum of linear factors using our factors of the denominator. So our denominator had 2 factors, x minus 2 and x minus 5. So I'm going to rewrite this as a over x minus 2 plus b over x minus 5, where we're saying, okay, there were 2 constants, a and b, that when we added these 2 fractions together, we ended up with 1 over x minus 2 times x minus 5. So what we'll do next is we'll, quote, clear the denominator. And so what that means is we're going to find common factors, basically. All right, and we're going to rewrite this fraction, 1 over x minus 2 times x minus 5, as a times x minus 5 over x minus 2 times x minus 5. So what I did was I took this, this factor that was over the b, or that b is divided by, and I'm going to move it into my numerator here. So I'm finding our common factors here. You'll notice, by the way, a times x minus 5 over x minus 2 times x minus 5 reduces down to a over x minus 2. I'm going to do the same thing with the b. So this is b times x minus 2 over x minus 2 times x minus 5. And the good thing about this is now we can actually combine our numerators because they have the same denominators here as right side. So what this means is since our denominators are going to be equal, our numerator will have to be equal as well. So that means 1 is equal to a times x minus 5 plus b times x minus 2. All right? So this whole process basically got us down to a point where we combined our 2 fractions back together so that we can figure out what a and b were. Now we're going to solve for a and b. We have a couple of options, but this is the easiest method that we call the heaviside method. And what we're going to do basically is we're going to take whatever our factor, make our factor equal to 0, and plug those x values in to solve for our other variables. So for example, I know that 5 is going to make my minus 5 equal to 0. So I'm going to plug in 5 first. And when I do so, I end up with a times 5 minus 5 plus a b times 5 minus 2 has to be equal to 1. So the a's are going to be multiplied by 0. The b is that 3b is equal to 1, so it needs to be 1/3. Next, we're going to set x equal to 2 next. The term with b is going to go away, and so I just get a 1 equals a times 2 minus 5. All right, so this means that negative 3a equals to 1, so a is equal to negative 1/3. So in other words, what we've done is we've said 1 over x minus 2 times x 5 is the same as negative 1/3 over x minus 2, that's the a part, plus 1/3 over x minus 5, that's the b part. And when you combine these fractions together, you end up with the original. So we've decomposed this fraction into 2 separate rational functions that we can then deal with. Another way of rewriting this is negative 1 over 3 times x minus 2 plus 1 over 3 x minus 5. Now why in the world would this ever matter? Well, because we've actually decomposed this in a way that makes it a simpler antiderivative to find. So now what we're saying is that when we want to try to find the antiderivative of 1 over x minus 2 times x minus 5 dx, we have just decomposed this fraction 1 over x minus 2 times x minus 5 into negative 1/3 over x minus 2 plus 1/3 over x minus 5. And so now we can rewrite our integral as the integral of negative 1/3 over x minus 2 dx plus the integral of 1/3 over x minus 5 dx. And hopefully you recognize these are easier antiderivatives to find. Whenever we have something in our denominator that's a linear power, a linear function, then we can find the antiderivative using natural log. Linear, ln, natural log. And so the antiderivative of the first part would be negative 1/3 natural log of absolute value of x minus 2 plus 1/3 natural log of absolute value of x minus 5 plus c. Okay, so we decompose this in a way that makes the antiderivatives easier to find. Now I can also combine this by taking out a 1/3 from everything. And then remember, if you've got a negative in front of a natural log, that means it can be put in the denominator. It's a negative power. And then we can combine the two of them because we are adding, really actually subtracting two factors on the inside. This combines into 1/3 natural log of absolute value of x minus 5 over x minus 2 plus c. Okay, example number 2. What do you do when you have three factors? So we've got x squared plus 3x minus 44 over x plus 3 times x plus 5 times 3x minus 2. So the first step will always be to decompose. It's not any different than what we did before. We just have three factors, so we'll have an a, b, and a c. So we're going to rewrite the rational as the sum of linear factors using the factors of the denominator. So what I'll do first step, I'll notice that I have three factors, so I'll write those as a over x plus 3, plus b over x plus 5, plus c over 3x minus 2. Okay. So then the next step looks a little complicated, but all we're doing is, for the first fraction, we want to recombine these together using the factors that we don't already have. So for example, the a over x plus 3 doesn't have a factor of the x plus 5 or the 3x minus 2. So I will include those in my numerator on my top here. So I've got a times x plus 5 times 3x minus 2, the other two factors. Same for b. It's missing the factors of an x plus 3, 3x minus 2, so that's get put in the numerator. And then c is missing the factors of x plus 3 and x plus 5. So I will combine all this together. So this looks really bulky, but the whole point is now all of my numerator is going to match with my numerator original, x squared plus 3x minus 44. Right? Because what we've done is we've matched up all our denominators. Okay? So when we've done that, now what I need to do is say, I need to solve for a and b. And I do so by finding where my factors are equal to 0. So I've got an x equals negative 5. That would make my a portion equal to 0. It will also make my c portion equal to 0. What it does not do is make my b portion equal to 0. So I plug in negative 5 into this portion right here, and I get a b times negative 5 plus 3 times 3 times negative 5 minus 2. All this ends up giving us 34b, which is going to be to what I want to plug in negative 5 into my right side of the equation here. So negative 5 squared plus 3 times negative 5 minus 44 will also give us a negative 34. So b is equal to negative 1. I'm going to do the same with the 3x minus 2 factor. When I said 3x minus 2 equal to 0, I get x equals 2/3. When I plug that in, I'll notice that the a portion goes to 0 because that has a 3x minus 2 factor already. My b portion goes to 0 as well. My c does not. So I plug in 2/3 into this, and I get a 2/3 3 and a 2/3 5. Long story short, they end up getting 187 over 9 times c. Plug 2/3 into my right hand of the equation. So we get a 2/3 squared plus a 3 times 2/3 minus 44. That ends up being negative 374 over 9. Simplify, get c equal to negative 2. Finally, a plus 3 factor equals 0 is the only term that negative 3 can go to 0 would be the a term. That makes sense because a term has the x plus 3 to begin with. So I have 3. I get a negative 3 plus 5. 3 times negative 3 minus 2. That ends up being a negative 22a. I plug that into my right side of the equation as well, and I get a negative 44. So a is equal to 2. So what does all this mean? Well, if I plug in a, b, and c, I get a 2 over x plus 3 minus the 1 over x plus 5. That's the b part. And then minus a 2 over 3x minus 2. So what we've done is we've decomposed this complicated fraction into three separate fractions, which is finding the antiderivative a lot easier. The calculus part's the really easy part. It's the decomposing part that's the tricky part. Okay, so what this means is, since I just found it on the previous slide, this decomposed into 2 over x plus 3 minus 1 over x plus 5 minus 2 over 3x minus 2. Then now I can split this integral into the integral of 2 dx over x plus 3 minus the integral of dx over x plus 5 minus 2 dx over 3x minus 2. Can I find each of these integrals separately? You bet. So this first integral is going to be 2 times the natural log of absolute value of x plus 3 minus natural log of the absolute value of x plus 5 minus 2 times natural log of the absolute value of 3x minus 2 divided by 3. Now I want you to think for a second why this last integral I would divide by 3. We just did a lesson on substitution. Is there an inside function here that has some sort of a linear factor that has a slope other than 1? Yes. So in order to counteract the fact that this derivative would involve a times 3, we need to divide by 3 out front here. And then, of course, our plus c. So again, the hard part was actually decomposing the fraction. Once we did that, we ended up with a nice, easy antiderivative here. We can also combine this into one statement. So the natural log of the absolute value of x plus 3 squared. So the 2 comes in as a power. And then everything with a minus is going to go in denominator. These are pre-calculus rules here. So our x plus 5 goes into the denominator. our 3x minus 2 raised to the 2/3 power has to go into the denominator as well, and then plus c. Okay, last example we'll do in this video. I assumed that what we're doing up until this point are what are called proper fractions or proper functions. In this case, in previous cases, we had an x squared over something ended up being an x cubed bottom. So the power was actually bigger on the bottom than it was on the top. If the power is the same or bigger in their numerator than it is in the denominator, we have to make it into a proper fraction first before we can use partial fractions. What's our technique for doing that? Long division. Okay, so we're going to end up talking a little bit about long division here in order to make this work as far as finding the antiderivative. So what I need to do is figure out when I divide squared plus 4x minus 5, the x cubed plus 5x minus 4. Okay, so for division, right here, basically what we're going to divide x squared divided into x. And I say x times x squared times 4x minus 5. All right, somehow this got like erased here, so we end up with an x cubed minus sorry. So we get an x. Okay, ignore that little part here. So I found x squared going into x cubed, it got us an x. So then I take this x and multiply by every term in the divisor here. So x times x squared times plus 4x times an x minus a 5 times an x. All right, so that gets us an x cubed plus a 4x squared minus a 5x. We change our sign, just doing regular division. Carry down, we end up with a negative 4x squared plus a 10x minus a 4. X squared goes into negative 4x squared, negative 4 times, so we get a negative 4 right here. And then we say negative 4 times an x squared gives us a negative 4 squared minus a 4 times 4x, which gives us a negative 16x. And then negative 4 times negative 5 gives us a 20. We change our signs. That's what I already did right here. And so we end up with a 26x minus a 24. X squared's not going to 26x evenly, so that becomes our fraction right here. So you get x minus 4 times plus 26x minus 24 over x squared minus 4x minus 5. From there, what we're going to do is we're going to use our partial fractions again on what the remainder is. So I know 26x over minus 24 over x squared plus 4x minus 5 has to decompose into a over x plus 5 plus b over x minus 1. We already went through the whole process, but basically what we're going to do eventually is we're going to get a times x minus 1 plus b times x plus 5 has to equal to 26x minus 24. Let x is equal to 1. That'll mean that 6b is equal to 2 when I plug all that in, so b is 1/3. If I let x equal to negative 5, we get negative 6a equals negative 154. So I plug in negative 5 into this portion on the right side here, so a is 77 over 3. So altogether that means that this decomposes into x minus 4 plus 77/3 over x plus 5 plus 1/3 over x minus 1. So we've done the hard part, that's the decomposing. Now what we've done is we've made it a proper fraction, and we've decomposed the rest of the fraction part. So we need to find the integral of x minus 4 plus 77/3 over x plus 5 plus 1/3 over x minus 1. The calculus part is the easy part. Antiderivative of x squared over 2. Antiderivative of 4 is negative 4x. And then this antiderivative of 77/3 over x plus 5 is 77/3 times natural log of absolute value of x plus 5 plus 1/3 times the natural log of absolute value of x minus 1 plus c. Woo! One way you can rewrite this is x squared over 2 minus 4x plus the natural log of the cube root of everything. So everything is a 1/3 power. And then we got an x plus 5 to the 77th times x minus 1. So that's to the first power. So this would be another way of rewriting this. Whew, that's a lot. We're going to do plenty of examples in class, but I wanted you to get an idea of what we got with partial fractions here. So in summary, in order to solve integrals that are rational functions that have factors that we can get out of our denominator, we use integration by partial fractions. First, we need to make sure any rational functions are proper. That was what example number 3 was about. And then we use the partial fraction decomposition process to break up any factors. And many answers will involve natural logarithms. They might involve other sort of functions, as we'll see in class. But I wanted to give you a preview right here of what we're going to see. Thanks for listening, and we will see you on the next video.